Here is the answer for the Day 2 bell work. Lead 2 sulfide, which has the formula PbS, has a KSP value of 3.0 times 10 to the negative 28th power. KSP stands for the solubility product constant. Capital K is often used in mathematics to represent a number that is a constant value. The solubility product refers to this ionic compound dissolving in water to create the ions that are in the compound, specifically lead cations and sulfide anions. When the substance dissolves, it will create a certain amount of lead cations and a certain amount of sulfide ions. If those two amounts are multiplied together, that's the product that's referred to by saying KSP, the solubility product constant. The question is, what is the concentration of the lead ions in a saturated solution of PbS at 25 degrees Celsius? This problem has a few steps. In step 1, let's write the dissociation equation that represents what ions are created when lead sulfide dissolves. So here is the equation. PbS solid produces lead positive 2 ions dissolved in water plus sulfide negative 2 ions dissolved in water. That's the dissociation equation. It indicates that this ionic compound dissociates into these two types of ions. And this is a balanced equation. There's a 1 in this position and a 1 in this position if there is a 1 in this position. Step 2, substitute into the general equation for the solubility product constant. And I typed that equation right here in blue ink. A KSP value is equal to the concentration of ion A raised to the x power times the concentration of ion B raised to the y power. The brackets in chemistry class refer to concentrations. They refer to the amount of ions that are dissolved in the given quantity of water. The letter X is the coefficient in the equation for ion A. In our problem, if ion A is referring to the lead ions, then there's the value of X, the coefficient 1. The letter Y right here is the coefficient of whatever the B ions are. Well, in ours, we're letting the letter B represent the sulfide ions, and the coefficient in front of that is the value of Y. In this case, it's a 1. So let's make our substitutions. For KSP, we'll fill in the number given to us in the original problem. For the letter A, let's use the lead positive 2 ions. And for the letter B, let's have that be the sulfide ions. X and Y are 1s because of this coefficient and this coefficient. That creates this equation. This part right here is our substitution for this. This part right here is our substitution for this. And this number right here is what we're substituting for KSP. Now in step 3, let's treat that like an algebra class equation and solve it. And what we want to solve for is the concentration of the lead ions. Remember, the brackets mean, in words, concentration of. So when you see this, you're not thinking in your head like brackets Pb2+. You're actually speaking in your head the concentration of lead ions. From our dissociation equation, we can see that there's an equal amount of lead ions created as there is sulfide ions. I know that it's an equal amount of each because they both have the same coefficient of 1 in front of them. So in place of the concentration of the sulfide ions, we can put something that's equal to that, which is the concentration of lead ions. Now in math class, what did you learn that you could do when you are multiplying two identical things together. That's called squaring. That's using an exponent of 2. So we can rewrite this as the concentration of the lead ions raised to the second power. Then, in algebra class, how did you learn to remove squaring? What is the math operation called that is the opposite thing of squaring? It's called square root. When you take the square root of this, the squaring cancels, and you're left with the concentration of lead ions. And when you take the square root of the right side, you get a square root symbol surrounding that value that was on the right side. The only thing left to do is to take a calculator and type that square root in and actually get the final answer. The result when you round it is 1.73 times 10 to the negative 14th power. This value is the concentration of lead ions that are created when the maximum amount possible of lead sulfide is dissolved in water at a temperature of 25 degrees Celsius.